Yes, Lynette? Neha? Neha?
Yes, teacher.
How are you, Neha?
Teacher, I'm fine.
You're fine, eh?
Yes.
Are you understanding?
Yes.
Good. All right. So now let's look at that one is for. That one is for. That one is for liquid. What about for glass block? What about for glass? Another subheading? An experiment. An experiment. An experiment. An experiment to determine. An experiment to determine refractive index. Determine refractive index. An experiment to determine refractive index of glass using real and apparent depth. Using real and apparent depth. So for this one, what do we need? What are the requirement members? Apparatus, the requirement that we need are, we need a glass block. We need a glass what? A glass block. We also need a retort stand. We also need a retort stand. We also need a retort stand. Then we need 2 optical pins. 2 optical pins. Then white sheet of paper. We also need a white sheet of what? Paper. I remember the other time I've explained why we need a white sheet of paper. Then we also need a half-meter rule. A half-meter what? Meter rule. This one is for taking measurements. This is for taking measurements. What is the diagram? What is the setup? Let's look at the setup. Let's look at the setup. So that's our setup. Okay? So that is the set what? The setup. Can we draw it? Can we draw it? So can we draw that? All right. So there's not much difference from the setup. The only difference here, the other one we are using a beaker, but this one we are using a glass. We are using a glass block. We are using a glass block. So everything is on the table. Is on the table. So you can see that with the way we have sketched it from there. So it doesn't matter. The position of the glass block doesn't matter. The position of the glass block doesn't matter. You don't need to cram the diagram the way they put it there. What is important? The features in that diagram. Features in that what? In that diagram. The features in that diagram. So I can put my glass block to be this side. I can put my to be this side. This one like this. And this one will come like this. Like that. Mm-hmm. So this is the other side. Mm-hmm. And it's resting on a table. It's resting on a table. So you can just sketch it like this. You can just make it that one flat. Just like that. Then from one point. So down here, you put it just beside. You just put it, don't put it on top. You just put the glass, the optical pin just beside it. Just beside it. And it must be touching one side of the So you can put it here. So assuming this is our pin, this is our pin, this is our pin, members, this is our pins. That is one of the optical pins. I already explained why do we need it to be touching, so that it becomes very easy for us to adjust the pin. So then one end here, we have a retort stand. Here we have a retort stand. We have a retort stand there. We have a retort stand. So that is our retort stand there. So that's our retort stand. So you clamp it to a given point, you clamp it. So this is where we have clamped it. This is where we have clamped it. This is where we have clamped it. By using the placing. So this is the pin which is outside. So this is the pin which is outside. You have clamped it there like that. Like that. Let me shade it so that you can see it clearly from there. And these two pins, they are of the same size. They are of the same what? They are of the same size. Now, due to refraction, this pin here will appear to be raised. Due to refraction, will appear to be what? Will appear to be raised. So you find out this pin here will be up to this point here. Will appear to be like this. Will appear to be up here. Will appear to be up here. Will appear to be like this. So the pin will appear to be like that. Okay? So this is what we are interested in. That's what we are interested in. So now the distance, the height of the glass block, this height here, this one here, or the thickness, this one now, sometimes we call it the thickness of the glass block. I can call it T. I can make it to be capital T to represent thickness of the glass block. Then from here up to this point, now this one will give us the apparent depth. This will give us the apparent depth, which I can call it small h. I can call it small h. Then from here to here, this is what we call apparent displacement. This is what we call the apparent displacement from here up to here. That's apparent displacement. Are you together, members? Are you together?
Yes, teacher.
Is it hard to do that? Is it hard to do that? Members, is it hard to do that? So the first thing, you first put a white sheet of paper down here, then you put a glass block on top. A glass block on top. So what are our procedures? We have said draw a line on a white sheet of paper and place a glass block. So this one you can use a writing on a glass block, or you can use the real optical pin. You can use the real optical pin. This one can be a writing. You can just get a piece of paper, a white sheet of paper like this, then just write a letter A on top. Then you just write a letter A like that. Then you place it. You find it's still going to be raised. The same experiment you can, but here we are using optical pins. For the lab setting, we use optical pins. So we say draw a line on a white sheet of paper and place a glass block above it, as shown in the diagram. Look down at the edge of the glass block, perpendicular to the tip of the line drawn on the paper. Adjust the surge pins. This is what we call the surge pins. This one we call it the surge pins, because we are using for adjusting until there is no parallax. Until there is no parallax. Ensure that no parallax. Ensure no parallax. That is, the pins and the image of the line should appear to be one. Should appear to be one. In other words, they should appear to be in a straight line. They should appear to be in a straight line, moving the head to and fro from the line of the observation. Measure the distance A and B respectively to determine the apparent depth of the line. As simple as that. So now we can now come here and say refractive index N, which is equals to Real depth of apparent depth. So in this case, what is our apparent depth? I mean, what's our real depth, members? According to this diagram I've drawn here, what is our apparent depth and real depth? Who can give us? Who can give us? Grace. Grace? Yes, Lamuno. Lamuno, what is our apparent depth?
H, small h.
Then our real depth? Our real depth is it?
T.
Then now refractive index will be equals to, according to the formula, will be
T minus h.
T minus H?
For the apparent
Refract-
displacement.
Yeah, for apparent displacement. What about refractive index? Refractive index will be
T over h.
T over H. Good. Good. Members, have you seen that? Members, have you seen that?
Yes.
So that's how simple it is. And it's a very common question. So just a matter of understanding the concept. Once you have understood the concept, description will not be a problem. And I said, when you are describing experiment, you don't explain experiment, you describe experiments. You give the steps. You give the what? The steps. You don't describe, or you don't explain the experiment, but you describe the experiment. Is that clear, members? Is that clear?
Yes.
Good. Good. So when you come back to school, we shall do this thing practically. We shall do them what? Practically. We shall do them practically. But this one you can do from home. Members, can we do this one from home? This one of water. This one here. Can we do it from home? Members, we can do this one from home. Can we try that? I want us to determine the refractive index of water. Refractive index of what? Of water. Assignment. This is assignment. Determine the refractive index. Determine the refractive index of water using available materials. Using available materials at home. At what? At what? At home. So what we said, what do we need? What were our requirements? What do we need in this? Members, what I just need you is, if you don't have a beaker, you can use a glass. You can use this transparent. We all have glass at home. We all have glass at what?
home.
Do you have glasses at home? This one you use for taking water. Do we have them, right?
Yes.
Yes. Get a glass of water. A glass of what? A glass of water. Then also what you need, this time you may not have the optical pin. You may not have the optical what?
Yes.
Pin. So what are we going to use as our optical pin? You can use toothpicks.
You need to.
You can use what? Toothpicks. Okay? Members, you can use what? You can use toothpicks. Or you can use a needle, if you have a needle. Okay? Okay?
Yes.
You can use what? You can use what?
I need it.
You can use nails. Okay?
Yes.
Yes. What else do we need? Now, this time you are going to use a ruler. You need a long what? A long what? A long ruler. Instead of having a what? Instead of having a half-meter rule, you are going to use a what? A ruler. A long ruler, okay? Yes. Then you look at the setup. You get a glass of water there. This is a glass of water. A glass of water is there. So you pick one of the, whether a toothpick, whether a needle, whether a nail, you put it inside the water. You put it at the bottom, beneath the water. You put it beneath, and it must be touching the edge of the glass. It must be touching. Then one of them, now because for you don't have the what? The retort stand. Use your hand as a retort stand. So keep on adjust until when you are looking from above, you must be seeing from above here. You must be seeing from what? Above. So adjust. Move this one until you see that as if they are together, because this one will be above. This one will appear to be raised from water due to refraction. So adjust this one. Then where you see that they are the same level, when there's no parallax. When there is no what? When there is no what? Parallax. Then put a mark at that point. Put a mark on the glass at that point. Then measure the height. Measure the height. You can put it full. You can put it full. You can put it what? You can put it full, or you can put it at a given height. It is not a must that it must be full. So you measure the height of the water. You measure the height of the water in the glass, like that, from here up to here. Then this one is going to present. This one is going to present what, members? It's going to present real. It's going to present real what? Real depth. Then at a point where they are coinciding, you are first going to measure from here to here. This one is what? Members, what is this? This is apparent what? Apparent displacement. Apparent displacement, sorry. Apparent what? Displacement. Then from apparent displacement, you can get apparent what? Apparent depth. Then I want you now to prove, we said refractive index of water is what? Who can remember? Who can still remember that? What is the refractive index of water? Yes, we said refractive index of water is what? 1.3 is 1 point what? Members.
1.3.
It's 1.33.
Excuse me, teacher.
Yes, I want you to prove this, but I want you to prove this practically. I want you to prove that.
Yes, teacher.
Yes.
Teacher, I have a question.
Who is that? Who is talking? Who is talking?
It was
Yes?
Shelly.
Yes, Anua.
Shelly.
Anua, your network, Anua.
Teacher, I had a question. My network.
Yes, even up to now, your network is still disturbing. We can't hear you well. We can't hear you well. Yes? Maybe can you type it and put it in the chat? Then I will be able to see. Type it and put in the chat. Okay? Even seriously disappeared. Lamuno,
Yes, teacher.
are you going to do my experiment? Are you going to prove it?
Yes.
What about Redi? Redi
Yes, teacher.
says something. You have been quiet for so long. Can you say something, Redi? Have you understood the experiment, Redi? The two experiments, have you understood it?
Yes, teacher.
All right. All right. So members, is there any question on the experiment? Anyone with a question on the experiment? Both for liquid and glass. Is there any question on that? No question, right? Good. So now I want you to prove it. After proving it, you send, just get for me, measure for me the real depth. Measure for me real depth. Put the value there. Measure for me apparent depth, and put for me there. Get for me apparent displacement. Get for me displacement, the apparent displacement, and put for me there. Then find the value of refractive index saying real depth over apparent what? Apparent depth. If you have been very accurate, in your experiment, you must get 1 point what? You must get 1.33. This one, if you change it to fraction, is 4/3. It's the same as 4/3. It's the same as 4 over what? It's the same as 4/3. Okay. Anua is saying, I said you put a glass, you get a glass of water, then you measure the height of the liquid column or the water column. You measure that one represents the real depth. Then get a needle, a nail, or toothpicks. Anyway, whatever is available there at home. Or just a stick, or just a piece of stick. Just put it down, the one which is straight. Or a piece of a metal. We can put it down here. Then the needle, it must be touching the edge of the glass. It must be touching the edge of the glass. Then get the needle, get two of them. Then one, you keep on adjusting it outside until you see that they are coinciding, until there's no parallax between the two pins, the image of the pin and the one which is the outside. Then that one will determine where it appears to be like. Then measure for me that height. And that height will give you apparent displacement. Then from apparent displacement, you can use it to find the apparent depth. Then from apparent depth and real depth, you can use it to find out refractive index of water. You can now use it to find the refractive index of water. That's what I was trying to explain. Is it clear, Anua? Is it clear now? Is it clear, members?
Yes.
Good, good. So,
Teacher,
yes, please.
Katinaus, when you are sending you this real depth, the apparent depth, we just send the answers.
Yes, just send for me the answers. Okay?
Okay.
Or to make it much better, you can even take the photo of the setup. Okay? When you are doing the experiment, you can say, Mommy, can you help me and take the photo of this? I think that. Okay?
Yes.
Okay?
Yes.
Whoever is there at home to help you, say, please, I want you to see the glass. I want to see when you are doing the experiment. I want to see, you can even record a video of that. You can record a video. Okay? Are you together, members?
Yes.
Yes, you can record a video. I will be able to see. Please, actually, video is the best. Record a video. Record a video when you are doing the experiment. Okay?
Yes.
Yes, I want to see it before lunch. I want to see it before lunch. Subheading. Effect of refraction. Effects of refraction. Effects of refraction. Effects of refraction. Effects of refraction. Number one. I remember this one we have discussed it sometimes back. Who can still remember them? I remember we talk about a swimming pool. We talk about the images formed in a glass block. We'll talk about a stake appears to be bent. Who can put it better now? Those are the things we look at, not so? Not so, members?
Yes.
Those are the effect of refraction. One, it makes a stick. It makes a stick placed in water. To appear. It makes a stick placed in water to appear bent at the point where it enters the water. It enters the water surface. It enters the water surface. It makes a stick placed in water to appear bent at the point where it enters the water surface. That is one. Then the second one, a swimming pool. A swimming pool. For a swimming pool, it appears what? It does appear shallow, not so? A swimming pool or a pond appears.
Yes, shallow.
Appears what?
Shadow.
It appears shallower. Okay? Appears what?
Yes.
Shallower
Shallower
than it actually is. Than it actually is. That's also another effect of refraction. Then the third one, an object placed at the bottom, placed at the bottom of water, placed at the bottom of water container, appears to be closer to the water surface, That's also another effect we normally see with refraction of light. Then the fourth one, an object placed below a glass block, appears to be raised, when observed from above, appears to be what? Appears to be raised when observed from above. Is that clear, members? Is that clear?
Yes. Yes.
So the details, that one we have already explained it. Because of refraction, you can see that one we have already explained all that. So you can follow that from the notes. I remember explaining all this. So this is what they're explaining. So a ruler or a stick appear to be bent when observed from above. You can see that. You can see from our diagram there. A coin or an object placed at the bottom in a container, still you feel that it still appear to be raised. All that is because of refraction. The twinkling of stars in the sky. You can see that. This is also another one. You add this one. This is the fourth one. Add this one. The tinkling of the stars. So let me try to check a video of that. so that we can see the tinkling. The tinkling of the stars in the sky. At night. At what? At night. So let me check a video for that. So that we can see. Let me check a video of that. Tinkling of stars.
Edit. Okay, so here's my
atmospheric refraction, twinkling of
Members?
Yes,
Yes,
teacher.
teacher.
Members, can we follow this video? We are just summarizing. I thought we are through with the lesson. Let's just summarize this lesson with the following what we call the tinkling of stars.
stars. Night sky
Members, can you get the audio well? Is the audio clear?
Yes, teacher.
All right.
is very beautiful. It is consist of different objects. Some of them are stars, while others are planets. Looking at the night sky, can you figure out if the object is star or a planet? Yes, you have been learning it from your childhood. The objects which twinkle are stars, and the objects that do not twinkle are planets. The question in today's discussion is, why do stars twinkle? Basically, the reason behind the twinkling of stars is atmospheric refraction. Let's learn how it happens. We live on planet Earth. The atmosphere of Earth consists of layers of air. The particles of air are closely spaced at the surface of the Earth than these at higher layers. That means the density of air is highest at the surface while it goes on decreasing towards the top layer. Now let's talk about a star. A star have its own light. Since they are at far distance from the Earth, therefore looks point-sized and so are treated as point source of light. The light coming from star, that is a starlight, when enters in the Earth's atmosphere, layer by layer, it experiences increasing density and so bend towards the normal at the boundaries between the layers. When it comes to us, we observe the star to be slightly higher than its actual position. Now air is fluid. It has property to flow. So, there are continuous and random variations in every layer of the atmosphere. These changes result in the random change in refractive indices of the layers. So, if refractive indices of these layers are not steady, how will the apparent position of stars?
Members, are we together?
Yes.
Remember now, this one we are explaining now the basic of refraction. Remember we said refraction is the bending of light rays, which is caused due to the change in speed of what? Light. Due to change in speed of what? Light. And what causes this change in the speed of light? Because of the difference in optical what? Difference in optical what? Densities. Due to difference in optical what? Densities. So we are comparing the surface of the Earth and the space. Remember, at the surface, here we have air is at I what? Air is at I what? Density. But in the one in space is of low what? Low what? Low what? Density. Of low density. That's why air is able to rise. The one that is rising up is of low density. Then the one which is more dense, like the moisture, the dew, we see that is of high dense. That's why you see is on the surface of the Earth. But the one which is less dense is in space. The one that you see they're now moving as the moving wind is those one of low density. So refraction is now when we see the stars at night, the position where we see the stars, that's not the exact position. Okay, that's not the exact what position. But what we are seeing is due to refraction. It appears to be close, but it's very far. It's very what? Far. And the actual position is not the same like the one we observed. Because, and now that position now what we call the actual position is not the same. That is now the tickling what we are talking about. It's not the same. It's not the what? The same. And what is causing that is because of the difference in optical densities. And the stars is acting as a source of light because remember we look at also sources of light. And star is one of them. It's one of the natural sources of light. Okay? Okay? Are we together, members?
Yes.
Yes. So you have to take note of that. So let's continue. Let's finish the video. Let's finish the video.
Are appear steady. The apparent position changes slightly but randomly. Similarly, because of random changes in refractive indices, the brightness of light coming from star also appears to be changing. The resulting effect of changing apparent position and changing brightness causes star to appear twinkling. Why do planets do not twinkle? The reason is simple. Planets are much closer to Earth. They reflect light falling on them towards us. Since planets are much closer to Earth, they could not be considered as a point sources. Large number of rays coming from such objects undergo refraction in random manner. But while reaching at observer, they nullify each other's effect. That means neither the position of planet change nor there is change in brightness of light coming from them. The intensity of incoming light does not change. It remains constant, and so planets don't twinkle. I hope you have understood this concept very well. Thanks for watching this video. Have a look at the range of courses available in variety of formats.
Members, my dear student,
Yes, teacher.
I believe you have understood refraction now very well, right?
Yes.
So when they ask you why is that the earth does not twinkle, what will you say? Or why do planets do not twinkle? Because the planet is very close to the what? It's very close to the what? To each other. They are very close to what? Each other. Okay? Are you together?
Yes.
And they do not produce their own light. Planet does not produce their own what? Light. So that's why it's very hard for us to see. To see the effect of refraction between the planets. Between what? Planets. That's why the position of the planets does not change. The earth does not change. The position does not change. Okay? Are you together? But galaxies and small like stars, for them they can change position because they are small and they are very far away from the space, from the earth, from the planet. They are very far away from the planet. And they can produce their own light. They can produce their own light. And because of that, and due to the difference in densities of the air on the Earth's surface and in space, it will cause refraction. It will cause what? Refraction. So it will bend. Remember, air around this Earth's surface is denser than the air in space, which means when light comes, the brightness from the star keep on decreasing. Keep on what? Keep on what? Decreasing. Are you together? The star is brighter than the way we see, is brighter than that. The only that way we see, what we see is not all that very bright. It's not all that bright due to refraction. Due to what? Refraction. Are you together, members? Are we together?
Yeah.
So tomorrow they may ask you, why do planets do not twinkle? You have the answer. Why does the sky or why does the stars twinkles? You have the answer for that, right? Do you have answer for that now?
Yeah.
Members, do you have answer for that?
Yeah.
Very good.
Yes, teacher.
Very good.
Yes.
Members, we have only 1
Yes.
minute remaining. We have only 1 1 minute remaining. So now, next time when we meet, we shall look at, write this heading down, write this heading. Refraction through a triangular prism. Refraction through triangular prism. Refraction through triangular glass prism. Refraction through triangular prism. Okay?
Yes.
Members, our
Yes,
time is
teacher.
done. Bye.
Bye. Bye-bye.
Love you all. Take care of yourself. And I will be waiting for my video. I'll be waiting for my video. I want to see how people will be doing the assignment. Okay?
Okay.
All right.
Teacher,
Bye. Bye.
Bye.
Mm.